shared by the two z-axes, like in this diagram. The positive direction of xi is arbitrary, so in this case we could have had xi facing into the page rather than out of the page. And the origin of reference frame I generally is naturally put at the intersection of the zi minus 1 and zi axes. But it can, however, of course, be anywhere along the zi axis. And in this case, the a parameter for the dh parameters is always 0, and this is good, makes our life much easier. And in this animation you can see us moving the xi axis to potential locations, pointing both into and out of the page, but ending up at the most natural location, which is the z axis intersection point. So once you've drawn your diagram and you've labelled all your axes according to this set of rules, you actually need to find the values of these 4 DH parameters for each reference frame. So the a subscript I parameter is just the distance from the previous z-axis to the current z-axis, or zi minus 1 to zi, measured in the xi direction. The angle alpha I is the angle from the zi minus 1 axis to the zi axis, measured rotating around the xi axis. The di parameter is the distance from xi minus 1 to xi, measured along zi minus 1. And the angle theta I is from xi minus 1 to xi, measured about the zi minus 1 axis. One important thing to note, just to minimize mistakes, is that 2 of these parameters are measured about the I reference frame, and 2 of them are measured using references in the I minus 1 reference frame. So we'll do an example of assigning the appropriate reference frames and then finding the DH parameters for the robot shown here. So this is a 3-joint robot. The first 2 joints are revolute joints. Joint 3 is a prismatic joint, and then you've got your tool point at the end of the robot arm. So we've assigned the 3 z-axes first. Z0 is the axis of revolution around joint 1. Z1 is the axis of revolution around joint 2. And Z2 is the axis of translation, or the prismatic axis of joint 3. To assign the x1 axis, which is located at joint 2, we need to note that the Z0 and Z1 axes intersect, and that x1 has to be perpendicular to both of these axes. The direction, whether we put it into the page or out of the page, is arbitrary. In this case, we've put it out of the page, and then using the right-handed rule, we can work out that the y1 axis must be pointing downwards. For the reference frame 2, we note that Z2 and Z1 once again share the same plane. They intersect. So the direction of x2 has to be perpendicular to both Z1 and Z2. So we have x2 pointing directly upwards, and then using the right-hand rule, we can work out that y2 has to be pointing to the left. So where do we put the origin of reference frame 2? Well, the natural location for it, when the Z1 and Z2 axes intersect, is at the intersection of Z1 and Z2. So that means that our reference frame 2 is located at the same point as our reference frame 1, as in the diagram. Reference frame 3 is the gripper reference frame. Z3 is the approach direction that the gripper moves towards an object in. Y3 is the direction that the gripper opens and closes against, and then using the right-handed rule, once again, we can work out that x3 must be pointing upwards. So let's work out the parameters by using our 4 rules for finding the DH parameters. So A1 is the distance from Z0 to Z1, measured along the x1 axis. However, in this case, z0 and z1 intersect each other, and in this situation, a is always 0. Alpha is the angle from z0 to z1 measured around the x1 axis. So if we look at the x1 axis and look at how much the z-axis has rotated, we can see it's rotated negative 90 degrees around the x1 axis. So alpha 1 equals negative 90 degrees. d1 is the distance from z0 to z1, from x0 to x1, measured along the z0 axis. So this corresponds to that 3 meter measurement. So d1 is 3 meters. Theta 1 is the angle from the x0 axis to the x1 axis measured around the z0 axis. So x0 and x1 are currently aligned, so the angle is 0, and because this is our joint variable, this is also our q1 variable. And you can go through and do the same process to work out the DH parameters, the 4 DH parameters for the second reference frame and for the third reference frame, and you should get the answers on this slide. The next step, of course, is once we've got these 3 sets of 4 DH parameters, we need to find the actual A matrices so we can work out our overall transformation. So for each set of 4 DH parameters, we plug them into our general DH matrix, which is shown at the top right, and for each time we do this, we'll get an A matrix. So we'll get an A1 matrix representing the transformation between reference frames 0 and 1, A2 for transforming from reference frame 1 to 2, and A3 for transforming from reference frame 2 to 3. And you should get these values shown on this slide. Because matrix multiplication is associative, we can do it in bits, different bits at once. So we'll do, we're trying to find the overall T subscript 3 superscript 0 transformation matrix, which is A1 times A2 times A3. But what we can do first is just find the transformation matrix between reference frame 2 and reference frame 0, which is just A1, A2. So these are the A1 and A2 matrices that we worked out in the previous slide. We multiply them together, and we get a slightly more complicated matrix. And then if we substitute in the actual DH parameters, so the DH parameters corresponding to reference frame 1 and reference frame 2, we can get the actual numerical matrix at the bottom right. To finalize the transformation matrix, we can go back and add in the A3 matrix into our multiplication. So we have the T subscript 2 superscript 0 matrix on the left, multiplying the A subscript 3 transformation matrix. We multiply these two together, we start to get some slightly more complicated terms in our new matrix, but there it is written down at the bottom. Notice in this case I've gone back to using the symbolic representation of the T subscript 2 superscript 0 matrix. And that's what we get at the end. Once again, if we actually substitute in the parameter values for a joint variable theta 1 equals 0 and a joint variable theta 2 equals 0, then we and L3 leave as a unknown, just as a variable, then we get this simple matrix at the end, which is our overall transformation matrix between reference frame 0 and reference frame 3. So the second part of this lecture, which is a little shorter, is to do what we've just done in reverse. So this is known as the inverse kinematics problem, and this is for working out how to set your joint angles and so forth in order to achieve a certain tool point position and orientation. Now, there's really no good universal black box sort of way of approaching this. So what we're going to do is take an approach based on geometry and a bit of trigonometry, drawing diagrams and working that way. And we'll make our challenge a little easier for ourselves by decoupling the position and rotation expressions from the overall transformation matrix. So the overall transformation matrix has this general form where you have the rotation part of the matrix R at the top left, and at the top right you have the displacement component of your transformation matrix. For many robots, and these are the robots we're going to focus on because it makes our problem a lot easier, the orientation is set by the wrist at the end of the robot manipulator. That means for us, all we have to worry about is the position, which is set by the first 3 joints in the robot. So that's the problem we're going to address. It's a subset of the larger problem, but often it's the main one we need to focus on. So it's reasonably valid for a large number of situations. So this geometric approach has a few sort of assumptions or things that we rely on to make it feasible. We rely on only having orthogonal twists, and also hopefully many zero-length parameters to make the math a bit easier. The general approach is what we do is we project the parts of the robot we're analyzing onto planes in order to find simple geometrical relationships in terms of angles and so forth. And as we're using angles and also inverse trigonometric functions, the general idea is not to use a cos, a sine, or a tan because they are not great in a programming sense. The ideal one is a tan 2, which is a function which you can find in programming languages, which takes 2 arguments, x and y, to work out an angle. So on the right of this slide, we've got a schematic or a bit of pseudocode. Well, it's actually pretty much real code in C code that shows you the a tan 2 function, and it takes two function arguments, an x and a y, and this is how the function actually works. You can see some if statements, and I'd encourage you to go through the function and see how it works. You might actually have to code this or something like this yourself, because it appears that robot C doesn't have an a tan 2 function. It only appears to have an a tan function. An a tan returns a value between pi on 2 and negative pi on 2. A tan 2 returns a value between pi and negative pi using a more detailed process, and most importantly, it works out which quadrant your angle is in, which is great. One thing to be very, very, very careful with when you're using a tan 2, or just in general, is to be extremely careful and double and triple check the order of the arguments that you pass to the a tan 2 function, because first of all, they're not always consistent between different programming languages, and second of all, a few years back, I think one of the major programming languages, the documentation for the a tan 2 function was actually wrong. It said that the arguments should be given in the opposite order to what they actually should be given in, which caused many people all sorts of headaches, including myself. So, what do I mean by using sort of geometrical analysis? Well, this is a simple example where we have a single revolute joint shown at the base of this robot in the diagram. It's got a second link, but we're not going to worry about that for the moment. What we're just going to do is project down from the tool point or the end of the robot into the XY plane. And that's what I've done in this top left diagram, and that corresponds to the planar cross section shown in the bottom diagram.